Why are you sitting there today and not there?
Oh, someone was there earlier.
Oh, that threw me off. I was like, who's missing?
If you want me to.
It just looks like Thomas isn't here. Neither is Christian. And is Nicole coming? No? All right. If you guys were to pick a day to skip lecture, this would not have been that day. So remember last class when we went over composites, how easy applying that concept of compatibility was? Right? Now, do you guys remember when we went over thermal expansion and the rod was bounded by 2 points and there was a temperature increase and that induced a stress and you had to find the stress? Is that easy or harder for you guys? Well, either way, today is an introduction to what is called static indeterminate members. Now, our focus today is going to be for axial members only, but we will get into potentially beams later on in the semester. So, let me first ask, who here knows what a statically indeterminate member is? You don't know?
It doesn't equal 0?
What do you mean doesn't equal 0? Indeterminate.
Yeah, something bad.
So all of the forces can equal 0. Let me ask this. What was one of the assumptions that you guys make in statics when you guys took COT 166, I think it is? Yeah. What was one of the assumptions that you guys made about equilibrium?
They're fixed.
Not fixed, but what were the 3 equations?
Some of the moments, some of the force in the x direction and the y direction.
Right. Now, that would be, a good example would be for like a beam that had a pin and a roller and then maybe some load, right? And then you could figure out what your reaction at A is and your reaction at B. Pretty straightforward, right? You guys know how to do that. This is what we call statically determinate. Now, what if I gave you guys... Oh, wait. Let me ask this. What is the one reaction that's missing from this member? AX. Which, of course, AX would be 0 if all of the loads were vertically downward, but it just gives you an idea on what the reactions are. You've got AY, BY, AX. Another example of a statically determinate member would be a cantilever beam, right? What were our reactions for the fixed end? You guys remember this?
All 3 of them?
All 3 of what?
Of the equations, a moment, x and y.
Yes. And then a moment. Now, how many equations are there? Great. How many reactions are there? 3. Lines up pretty easily and very nice, right? You could determine however many each reaction with each equation. So that is the definition of a statically determinate member. We can find 3 unknowns with 3 equations. Those equations being those up there. Now, a statically indeterminate member, on the other hand, would be something like if this was a fixed end here, it cantilevered off. And then one of the things about this that's different, other than maybe its length or whatever, is this new reaction right here. What are our reactions here?
Y is X in a moment.
Two y's. We are going to have an AY and a BY, an AX, and a moment. What's the issue here? Well, if you were to write out all of your equations, at some point you would still have two unknowns at any particular point, at minimum. So because of that, it's unsolvable using our three equations. Which means we need more. But then the question becomes, what other equations are there? And this is the fun part. Remember last class when we went into composites and we had two materials but only one force? We did it last class, right? We applied two concepts. We applied equilibrium, which you guys learned about in statics. And what was the other new concept that you guys learned about? There's a word for it. And I told you guys it. Compatibility. Which means we need to determine a deflection at a particular point and then enforce it to where that deflection satisfies our quote-unquote boundary conditions. So a good example of this would be, let's do just an example, just right away. All right, I'm gonna make it a nice, easy example. Let's say we've got a bar, and unlike previous bars, this bar is gonna be bounded on two ends. All right, I only showed the beams up here just for clarity purposes to describe what a statically indeterminate member is. But even with this right here, if you had a force that was located here, let's say it was 2 kips, and it was located, I don't know, 4 inches and 8 inches away, what would you say the forces are in each reaction? Well, you could probably use the naked eye to figure that out because this is a very simple problem for that. But once you start mixing materials within these problems, you start getting more complex answers. So because of that, I want to teach you guys just a general procedure to be able to solve for any particular problem. Make sense? So let's say that we need, I don't know, an elastic modulus of 29,000 KSI. This has just 1 square inch cross-sectional area. All right, so what do we need? First of all, let me ask you guys this. What do you guys think the reaction forces would be? Just looking at it. You could probably just do it in your head or on the calculator right now. without even applying any of the rules that we're doing. Olivia, any thoughts? No? All right. Well, here's what we'll do then. So, we have two unknowns, ax and bx, right? Now, we need two equations, right? One equation is going to define equilibrium. So let's write down an equilibrium equation. And then we have an equation for compatibility. What is our equilibrium equation going to be here? Sum of the forces is equal to what? If this is equal to 0. Look at our unknown reactions too. All right, just always assume they're moving positively to the right, and then the math will work itself out. You guys know that from statics. What's our equation going to look like, Emily?
AX plus BX plus 2.
Exactly. Now you guys notice, oh, we can't determine that. We have no idea what to do. So we need to enforce compatibility. If you guys were looking at this, what do you guys think would be a logical way of enforcing something? Would you guys agree with me that the deformation at A has to equal 0? The total deflection at A has to equal 0? Would you guys agree with me on that? What about the deflection at B? Would you guys agree with me that that has to equal 0 also? Right? You load this, you apply force here, and it pushes, all right? But there's a wall here. That wall is going to prevent any type of lateral movement of the bar beyond that point. So the idea is to determine what the change in position is at the point of interest that we are considering. So let's say we wanted to find the reaction Bx. All right? So if we want to find Bx, then we use the compatibility equation for the deflection at B equals 0. If we wanted to do it similarly for A, solve for AX. So what we're going to do is we're just going to apply it for BX, okay? Now, how do we enforce compatibility? Well, what we need to do is consider two separate systems. It's going to look very similar to the stuff that we did for thermal, and you can apply these concepts for thermal also. It's just a more formalized way of writing out everything. So, let's consider two systems. And these systems, when you add them together, are theoretically going to be the final system that's like up here. So what we have is a system with two kips of force and then another system but instead of it being the two kip force, what you're applying here is the reaction Bx. Now, the next step that we want to do is we want to find the deflection at B. And the reason being is because the deflection at B in both systems, so we'll call this system 1 and we'll call this system 2. When you add them together, have to be 0. What I mean by that is that this equation here, we assume that this deforms that direction, right? With Bx, it's going to deform in this direction, assumingly. But by throwing both of these into the equation, you'll be able to back calculate a value for Bx in such a way that it's negative. Right, because this will get crossed over to the other side. So Bx becomes negative because it has to be in order for the deflection to go that way. You guys agree with me on that? If you don't, that's fine. So let's do it here. What is the deflection equation going to be at this point here? How would we calculate this deflection, or that deflection here? What would that deflection equal? Remember your deformation equations for axial loads.
Is that NL over EA?
Exactly. But how many parts of this problem are there? Or of that member are there? 2, because the load separates it, right? So we're going to have an NL over EA for this segment right here. So I'm going to put 1A for that. This is segment 1A, and then this is segment 1B. Plus NL over EA 1B. Now, what you can do is you can draw out your shear force diagrams or axial force diagrams, and you'll be able to find the internal forces in each bar. All right? So let's do that really quickly. Just a review of everything that we've previously covered. What is the internal force in 1A going to be? You guys would agree with me that if we cut a section just like that, first we do external equilibrium. So what would the reaction at A be? What would this reaction be? It would be -2 here. So from external equilibrium, we would get AX is equal to -2 kips. So let's just redraw our diagram to just show that. So sum of the forces in X equals 0 equals AX plus 2. You get AX equals -2 kips. Next thing you do is you draw a force body diagram. All right, this is segment 1A. This is going to be our 2 kip force. And then we've got an internal force, N1A, right? What does N1A equal to? Yeah, 2 kips in tension. Let's do the same thing now. But now, oh man, I'm drawing it way too small, I think. You guys probably are looking at it like it's microscopic. Yikes, not that. So now we've got a 2 kip, and then our reaction of 2 kips. You cut the section, and now you've got N1B. But what is N1B going to equal? 0. Everyone see how I get those internal forces, right? It's just a repeat of the stuff that we've been doing. The only thing that's just kind of annoying is now you need to do it twice in one problem. And you'll see why. So, if we know that N1B is equal to 0, that whole thing equals 0, because it can't deform. So, delta B1, the translation in the total deflection of this point here, is entirely dependent on this part of the bar being loaded. So, we come over here now, and we write out our equation. Delta B1 is equal to, our force is 2 kips. The length is 4 inches. Our elastic modulus was 29,000 kips per square inch. And then our area was 1 square inch. What do we get for the deflection at B1 if it was unrestrained? What'd you get?
2.759 times 10 to the negative 4.
Does everyone get that? Great. That's part 1 done. Part 2 now is repeating the same process, but for the system on the right now. What is the total deflection at B going to be for system 2? Who can tell me? How many parts are there? 1 or 2? There's 1. So it's just going to be NL over EA. Conveniently, a lot of the times the internal force here is going to be constant because it's just a reaction force, so the force is just translated throughout the entire thing. So you only need 1 N, and then you just keep on adding on for every different material we have, which I'll show you guys in another problem. So, what is our internal force here going to be then? Not quite. What's the applied force that we're considering there? What? No. In this system here. The applied force in that system. BX. Exactly. Our force is BX. Because that's the unknown we're solving for. The length of the entire bar that's being loaded is then multiplied by 12 inches, and then 29,000 KSI times 1 square inch. Somebody calculate delta B2 for me. You just plug it into your calculator, just excluding the BX, because it's just going to be equal to BX times some number. And also, just so you guys don't get confused, I'm going to put circles on here as well, just so that way you guys aren't like taking squares or square roots, because I don't want you guys doing that. Did you get it?
Yeah.
What'd you get?
4.138 times 10 to the negative 4 inches.
It's going to be actually inches per kip. Is everyone following so far? Are there any questions at all with where we're going with this? No questions? Everyone's following? Good. All right. So we got both of our equations now. The next step is just plug everything up here. So you now have 2.759 times 10 to the negative 4 inches plus BX times 4.138 times 10 to the negative 4 inches per kip, and that equals 0. Now this just becomes an algebra problem, and you can solve for that reaction BX. What'd you get, Michael?
If I did this right, I got negative 1 point, say 50 times 10 to the negative 8.
Nope. Shouldn't be that. What'd you do? 2.759?
I subtracted the 2.7 over to the right
Yeah.
and then divided.
Probably just threw it into the calculator wrong. But you would basically get 2 points. What'd you get? Nope. What'd you get, Olivia?
Negative 0.6667.
Yes. Which is indicating what? That BX is actually moving to the left here. So we just need to rewrite BX is equal to 0.6667 kips to the left. Now, we solve for one of the unknowns. How many unknowns are left in this problem? We solve for BX. This is equal to negative 0.6667 kips. What's our last unknown? AX, which we can solve pretty easily now. AX plus negative 0.6667 kips plus 2 kips. And what you should get is 1.3333 kips negative. Does everyone follow along with that, how we get to this conclusion? Now, I've got a nice little trick for you guys. Whenever you only have one material, and it's loaded simply like this, if you want to find the left reaction, somebody with a calculator, who's got a calculator? All right, multiply 2 kips times 8 divided by 12.
Still 1.33.
What? 1.33? Oh yeah, 8 divided by 12. That's AX. BX is going to be 2 kips times 4 divided by 12. So, whenever you have a singular material only, and it's a very simple situation like this, you can just use proportionality to find it. By just assuming, okay, the load gets split to the 2 sides somewhat evenly, just through proportion. Now, if you guys have 2 or more materials, you can't do that. Because then the stiffnesses of each material attract different forces. Think of the stiffness of a material kind of like behaving like a magnet, where the stiffer a material is, the more force it's going to attract. Does that make sense? And then if you guys just wanted to draw your internal force diagrams, I'm actually going to drag this way down here and then just move this just right along to the side, just to keep things all in one. If we wanted to draw force body diagrams now, or internal force diagrams, so I'm going to write IFD instead, internal force diagrams, right? Our reaction at A was 1.33 kips, give or take, right? And so now we can determine the reaction in, I'm just going to add this point here and just call this NC, point C. So let's say we wanted to find the internal force in member AC. What would the internal force in member AC be? That sounded really weird. AC, what would the force in AC equal to? Not ACB. In tension or compression? Right. And now, let's do it again, but for now on a larger scale. We're at a different location. And now we've got NBC. What would NBC equal to? In what? Tension or compression? Wrong. It's going to be compression. Because it has to go to the left in order to balance out the 2 kips. You guys see that now? So, in total, our force body diagram, if I just grab this over here, and then I want to copy that, and paste. There we go. Now I'll draw out just a little diagram down here. I'll replace these with their reactions. So this was 0.667 kips. This was 1.333 kips. And then this was 2 kips. And then we don't really need that anymore. So we determined that AC was in tension. So that's 1.333 kips. And then we determined that BC was in compression as 0.667 kips. So now the bar is both subjected to tension and compression because of the fact that it's restrained now. It's a very similar situation to if you guys were considering thermal expansion, right? The bar can't expand anymore, or it can't laterally deform. So because of that, the restraints push back against it, which in turn causes an internal force to develop. It's the same exact thing here. The restraint here is pushing back on the bar, restricting deformation, which in turn is inducing additional force development. Specifically, a compression force. And that compression force is roughly 0.667 kips. Otherwise, we would be designing for a tensile force of 2 kips. Make sense? Are there any questions about this problem at all that we just did? Everyone follow along? Yes?
Can we do another one, but with 2?
Yes. I'm about it. And if you guys still have your get out of jails for today, those are the ones from last class also. It's just going to be the second problem. It's also 2 materials. All right. So let's do another example. And this time, it's going to be a bar, yet again. With 2 different diameters or 2 different dimensions and 2 different materials. This one I'm going to highlight yellow just so that way we can clearly see that it's kind of different. And I don't know. And it's going to be restrained here as well. And let's say that this force is just applied just right here, right at the intersection point. So we'll say that this is about 20 kips. We'll say, what do you guys want the first material to be? Just pick. What did you say? All right, so this first material is going to be A36 steel with a cross-sectional area of what? Or pick a dimension. Do you want it to be, do you guys just want to work with an area? I'll give you guys just an area because you can calculate areas pretty easily. So we'll say that this has an area of around 2 square inches. And then this has an area of around 1 square inch. And what is the second material, the yellow one? What do you guys want to use? Anything but any type of steel. Or any of the main structural steels. I'm thinking like yellow brass or copper. But that's only because I highlighted it yellow. What is it?
Annealed copper.
Yellow. Annealed copper.
Yeah.
Okay. All right. And then for dimensions, I'm going to say this is about 10 inches. And then this is about 8 inches. All right. Now, just really quickly, let's check proportionality. We're going to have a reaction A. We're going to have point C and B. So just really quickly, using that proportionality rule that I showed you guys, compute what AX and BX could potentially be. I'm going to show you guys why it's wrong, and we'll figure out why it's wrong, but I just want to show you guys why it is. Because it worked for the previous problem, it's not going to work for this one. But somebody just do the math anyways. What'd you get?
8.8889.
For AX?
Yeah.
And then you get 11.11 kips for BX. Right? Those aren't going to be the answer. But let's see how far we're off. All right? So, step one is identify our two equations. So, for equilibrium, what's our equilibrium equation going to look like?
Is it AX plus BX plus 20 kips?
Yeah. Oh, yikes, I wrote that way too small. Sum of the forces equals AX plus BX plus 20K, and that's all equal to 0. Can we use compatibility, or can we use equilibrium to solve for AX and BX? No, we cannot. So, compatibility we need. Let's look at compatibility. Where can we apply compatibility? Hint, it's going to be where we know the deformations have to be 0, or the deflections have to be 0.
A and B.
Yeah. So we can choose either A or B. Which one do you want to work with? Both will give us the same answer. It's just different methodology of solving it.
A.
You want to work with A? Oh, wow. All right. You're making...
Rather than B.
Nah, we'll work with A, since you just want to make my life harder. All right. I'm kidding. It's the same thing. So let's use A. And what this means is that the deflection at A has to equal 0. Our next step, which is basically just going to be like step 1A. There's going to be a lot of steps in step 1. So step 1A is going to be split systems. And what this means is we need to have two separate systems I'm going to copy that because I don't feel like redrawing everything over and over again. With our first system being entirely unrestrained at B. Nope, we said A. Entirely unrestrained at A. And then a second system, I'm just gonna, over here, where now instead of considering this 20 kip force, oh, yikes. Come on. There we go. Erase. What do we replace the reaction with? We replace it with its equivalent reaction, AX. So, what we need to find here, we'll call this system 1, and we'll call this system 2. We got to find delta A for system 1. How would we find that? I'm going to give you guys a few minutes to tell me what the internal force in each bar is for system 1. Because you guys should really know how to do that when you're solving these problems. It's like one of the most important things. No? Why not? This is like one of my favorite topics. Professor Simon doesn't do statically indeterminate structures, but I show it because every single building that you will ever work with is statically indeterminate. And there's a reason for that.
What's the reason?
If one of the supports fail, it's still statically determinate. Just the forces get transferred to different members, and then the members are usually over-designed to handle that type of failure. Yeah. So if this column were to fail, for example, the immediate area would fail, but the entire building wouldn't collapse because of it.
I like that building in the city. I think the chimney that fell down.
Yeah.
That was good. That's pretty good.
Mm-hmm. So it's important. The more redundant members you have, the better. But then the client gets pissed off when you have too many. Get the internal force here.
Is that right?
Not quite. Remember, we removed the left-hand reaction here, which means the only reaction is technically the one over here. So be careful with that. See, John wanted to make your life more difficult. So blame John for that.
But it gave me his calculator, so it can't be me.
All right. It balances out.
be an engineer.
Figure it out yet?
I'm just doing it.
Zach? Now, for you, I want you to find me the deflection at A.
Okay.
Just for this system, no. Don't do it for the redundant, yeah.
Alright.
Well, I'm just asking you guys to find the internal force of each of these, just for that number. That's all I'm asking right now. So just find the internal force. It's just to give you guys practice with it. Yeah.
Wouldn't this just be zero then?
The internal force?
No, no, no.
Deformation.
Yeah.
Because there's no internal force.
Exactly.
Figure it out.
We'll have to do it again because I got all mixed up.
You messed up. What'd you do?
I was trying to, looking back at these, I was trying to see if I could use, I'm trying to figure it out, yes.
Well, my recommendation is just apply static equilibrium. Just doing this part of the problem is just like solving a static problem, and then applying what we've done previously.
Okay,
The stuff that's like new and the thing that makes this problem, these statically indeterminate problems difficult, is just the amount of work that goes into it.
okay,
Alright, but everything we've learned so far, the only new thing that you've technically seen is compatibility for,
okay,
for this.
okay, so then,
What'd you get, John?
I mean, is that right?
Right, so then what is the internal force here and the internal force there? That's what I'm asking. Alright, we'll work on it so that way we can kind of like just move on. So, when you're solving for this, it's just a basic statics problem, right? First, so step one of this thing, so this is kind of like step 1, A.1, is just apply equilibrium. All right? So you've got the sum of forces in X equals 0, which is equal to 20 plus Bx. Bx is equal to negative 20 kips. From there, you apply step 1A.2, which is internal equilibrium. I'm going to just move this over here just to identify explicitly external versus internal. And what is our internal equilibrium going to tell us? That's when you cut the sections. So when you cut sections through each of the members, what are you going to find for the internal force NAC? What is the internal force in member AC? Would you guys agree with me that it's 0? Who here doesn't see why it's 0? Everyone sees why it's 0 then. Emily, Irving, Joseph, everyone sees it? Okay. Now if we go to NBC, what is the internal force?
20 kips compression.
What did you say, Edgar?
20.
In what? Compression or tension?
Tension.
You say compression, you say tension. Who here says tension? Joseph does. Who here says compression? Olivia and Michael and Emily.
Tension.
Now you say tension? Wait, you just raised your hand for compression and then you raised your hand and said tension. Which is it? I'm confused.
You're going this way first, and then I'll stick with compression.
It's in compression. All right? And those are our internal forces. We would determine those like we've been doing throughout the semester so far. Now, for the deflection equation, this is done through the same exact thing that we've been doing throughout the semester. The only difference is now we're finding a change in position of a particular point, which that delta A1 is going to equal delta AC plus delta BC. But I'm putting that little 1 circled on top to indicate that that's only a deflection for that first system. We write this out a bit more, and we've got N AC1 LAC over EAC AAC plus NBC2 LBC over EBC ABC. I'm not writing 1 or 2 for LEA because it's going to be the same in both systems. It's just a material property. The internal force in member AC is 0, so that just cancels out, which means that the change in position at point A is just going to be 20 kips in compression, so it's negative. Hold on. I don't think I like that. If it compresses, it's moving to the right. So 20 kips times LBC is going to be 8 inches. Divided by, what was the elastic modulus for BC? And then the area we said was 1 square inch. And the only reason why I'm not considering the negative 20 is because of the fact that since we're considering deformation going this way and this is compression, the deflection is going to be moving positively. So it's a little bit weird because of the fact that we're considering deflection on this side instead of on this side. Otherwise, usually the negatives would work, but because it's kind of like reversed or flipped, you have to consider the negative of it. It's weird. So just pay attention to which direction it would be deforming in whenever you're solving it. Otherwise, my recommendation is just always on the right-hand side because mathematically the numbers, negative or positive, will be easier to work with. So what do we get for the deflection at A?
0.0107.
All right. Now we do the same for step 1A dot 3, or 1A dot 1 now, for the same system. And what you would find is that the internal force is just going to be NAC2 is equal to negative AX, and then NAC, or BC2, is just equal to negative AX also. You guys see where I get that? This force is just applied at the far end, so that force is just going to be transferred all the way through. You guys see that? So it has to be negative AX for both of them. And so then our change in position for A, for system 2, is just going to be negative AX, but again, it's deforming to the right, so keep that as is, times LAC, which is going to be 10 inches divided by 29,000 KSI times 2 inches squared, plus AX times 8 inches divided by 15,000 KSI times 1 square inch. So really quickly, just determine what that coefficient is by factoring out the AX, then I'll give you guys a quick 5-minute break. What'd you get, Michael?
0.00137.
0.00137?
Yeah.
Not what I get.
We just put it in without AX, right?
Yeah. How'd you plug it in?
Make sure I did 10 divided by 29,000 times 2 plus. Oh wait, I put 18. That's why. I got 7.057 times 10 to the negative 4.
Yeah. Which is just the same as 0.000706. And then the units of this are inches per kip. All right, I'm going to give you guys 5-minute break, and then we'll finish up this problem, work on one more problem, and then I'll give you guys the get out of jail to work on. Who here likes this topic? I'm assuming no one. Oh, man. Oh, you're going to love the exam then. I put a mix of composites on this. I'm kidding, by the way. That would be too evil.
What's on this exam? Is it just everything we've been learning?
Everything we've been learning past exam 1.
Okay.
So that includes thermal, 3-dimensional stress strain, composites,
And then this.
static indeterminacy, and then whatever we're covering next week.
So the exam at the end of the month, basically?
Say that again?
The exam's at the end of the month?
Yes. Yeah, this is the hardest topic on the exam, and I understand that this question takes a little bit of time, so I don't think I gave you guys a really long statically indeterminate problem to solve. It's not going to be more than 2 members usually because they take time to solve. You know, as you guys can clearly see the amount of work that we're doing right now, because it requires you to basically solve an entire exam 1.
Right.
All right. He's just done. Are there any questions about this so far? You guys really like composites more last class? Next week we get into stress transformations. Those are fun. A lot of circles though. then I'm trying to like think. No, it wasn't torsion. Let me see. I gotta go back now. This. Most of the updates. Stress considerations, part 5 and part 6. Everyone's leaving. Am I that boring?
It's just a topic.
Just the topic.
So the next test is gonna be like 5 or 6 questions?
It's always going to be 5. 4 regular questions and then like the true false questions. It's always going to be that.
And it's at the end of the month.
I forget what day it is exactly. I think it's
Just the day before Halloween.
no. Looks like it's on the 23rd. So it's week before Halloween. So it's not exactly the end of the month, it's a little bit before that. Then did I have review topics in there for this accounted for? Let me just double check. Yeah, exam 2 review. Alright. We're just gonna wait for Christian to come back because everyone else left. How's everyone's day going?
Long.
Long?
Yeah.
You said it.
That's the end of the week, so.
Yeah.
How's yours?
I was in a meeting for 2 hours today for the segment aligning, stacking, and handling design calculations because we're apparently over 200% utilized. So we're like trying to figure out why it's going wrong. And we have people from our Canada office who are doing like a back check review of our calcs. And we've used this spreadsheet on like 5 different projects, and they're now telling us like everything is wrong. So it's like, okay, but people in Europe said we were right. So now there's just internal conflict in my company about who's right, who's wrong, and then just trying to address everything.
That sounds like fun.
It's not.
Do you work at a civil firm?
Yeah, we do a lot of really, we're like a design firm. We're not explicitly like, I guess, civil. I know we have a civil group, but we do a lot more than that. Like we have tunnels, we have aviation, bridges. Like, you know, all of the work on JFK, my company's the designers for certain aspects of that project. And then obviously Skanska is the construction managers, I think, on them. But everyone knows Skanska, right?
Yeah.
Yeah. Yeah, they're like the biggest company in construction. Anywhere you look in New York City, if you ever walk around, if there's construction going on, I guarantee it's Skanska. They're a good company to work for, I believe. So if you guys are looking for internships, that's a good company to apply to. No? Not for heavy civil? Ah,
Used to. Not knowing too much confidence.
pay a lot of money too.
I like residential.
That's not fun. Those are small projects. What?
It's the best.
Mm-mm. No way. I'm learning wood design right now, and I absolutely hate it.
Really?
Yeah, there's so many coefficients that you have to learn, like a wet damping factor, and then like thermal factors, and it's just applying a ton of factors. And I don't know wood design at all. I did not go to school to learn it, but I have to learn it for my exam. It's fun. All right, so everyone's back. So let's continue really quickly. The problem is almost done, I promise. The only thing we need to do is just delta A1 plus delta A2 equal to 0. And this is going to be step 2. So 0.0107 inches plus AX times 0.000706 inches per kip equals 0. I guess it's not step 2, it's step 1B now. And then somebody tell me what you guys get for AX. Olivia, you think Nicole's gonna like this topic? What's wrong with this topic?
How do you feel about full numbers?
It feels like it?
Yeah,
What do you mean?
so confusing.
All right. So after this problem, I'm going to ask you guys to help me to clarify certain things. So that way I can give you guys a better understanding. Because I'm asking if you guys are understanding, and you guys are shaking your head yes. But then now you're telling me, no, I'm not understanding a single bit of it. So now I'm confused. Because now I'm getting a yes and a no from the same person. So what do you guys get for AX?
Negative 14.15. Is that right?
14.15?
Yeah, did I do it wrong here?
What'd you plug in?
0.0107 divided by 0.000706.
I get 15.15. What else does everyone get? $15.15 kips. And what that means now is if we pull this up, and I'm gonna grab this again, and then I'm going to just drop this here, paste. All right, now let's apply our reaction forces. This reaction force was 15.15 kips. All right, to put that into perspective, I'm just going to write incorrect here. And then from correct answers, we have AX is equal to 15.15 kips. And then step 2 is just our equilibrium again. So you do summative forces equals 0, negative 15.15 plus 20 plus bx. You get bx is 4.85 kips negative. Everyone see how I got those numbers, right? The AX and BX through compatibility. Okay. Now you guys notice how much more different the answers are in comparison to using that proportionality? The reason being is because now we have two different materials, and clearly this material is much more stiff. And remember the magnet analogy, this is a larger magnet, so it's going to carry or attract much more force towards it. Does that make sense? If we use the stronger material here, then this will attract more force, which means this reaction will go up. And of course, you can play around with the geometries also. If instead we use the weaker material, but increase the diameter or the area significantly, then that'll attract more force. So it all just really depends on the stiffness of the material. All right, now, where are people getting confused about numbers coming out of nowhere? Please provide me some help so I can help you guys understand a bit more. Yes?
I'm still kind of confused about solving internal force.
Okay. So, for the internal forces here, let's work on that. I'm going to draw out the internal forces for it here. But do you guys understand the concept about removing the reaction and to make it like two statically determinate systems that when you add them together is a statically indeterminate system? Does that make sense? Removing the reaction, why we're doing that?
You could just pick either one.
Yes, you can pick either of the reactions. You could have removed B here, but we chose A here because John wanted to make our lives more difficult.
It worked out.
It did. But you guys understand why we're removing a reaction, right? It's a thing that we call superposition. And the reason we can do that is because of linear elasticity. For every given displacement, there's a known force. So as long as we are within a linear elastic regime, we can kind of treat it like it's a spring. So we're just kind of scaling up forces, almost. It's kind of hard to explain, but the reason we can split the two systems is because we're in a linear elastic region. So when you remove the reactions, you can just split them and just solve for each reaction as a separate applied force. Yes?
If we chose B, would basically, it would switch basically, so that would be the zero number.
If you chose to remove B, then yes. You would have gotten this as a zero force member, and then this would have been 20 kips in tension, which then you would have found the deflection at B, which would have been, it would have been 20 kips, whatever the number is.
Yeah.
But you would have, instead of finding 15.15 kips for the force, for the unknown force, Bx, you would have found it as the 4.85 kips. All right.
That makes sense.
So let's do the internal force really quickly. First of all, what we need to know is the external equilibrium. When we do external equilibrium, you will find that this reaction here has to be 20 kips. Everyone agrees with me on that, right? Everyone agrees that that reaction has to be 20 kips. If you had more than one load, you would just add on to the equations and just solve for the reaction force. Does that make sense? Okay. With that now in consideration, we draw the internal force diagrams. So let's cut a section right through member AC. So this is going to be section AC. And we have an internal force, NAC. And then I'm going to label this NAC 1 circle to indicate that this is for system 1. What are our applied forces in the system? Do we have any? We do, but is it in the section cut that we're considering? Remember, we're looking at everything to the left or right of a section cut. In this case, I'm looking at it, everything on the left of the cut. So our force is 0, right? And that comes from some of the forces in the x direction. If you were to look at everything on this right-hand side here of the section, and you applied a tension force going that way, here, let me do that. So tension force going that way. What do you guys notice about NAC1? Consider everything to the right of this cut. What does NAC1 equal to? Kips going to the left, 20 kips going to the right, 0. So, no matter how you cut the section, you should always get 0. This is when we were first learning about cutting sections to determining the internal forces, because that's the important step, is cutting those sections and analyzing everything to the left or to the right. It's the method of sections, like for trusses, but instead we're applying it to internal force analogy now. Does that make sense? Now, let's cut a section BC here. And now we can look at anything to the left or to the right of that section. I'm going to look at everything to the right, to the left, I mean. This is BC. This is all highlighted here. And then this here is 20 kips. And now we just add our tension force, NBC 2 is equal, not equal to 0, but we look at it. What does NBC have to equal? Negative or positive? Negative. So NBC 2 is equal to negative 20 kips, which means 20 kips in compression. And then you would just repeat that process for every single part. So you would repeat the process here. It's just convenient that this force is just always applied at one of the ends, because then the internal force is just shared between both. Because then the force just gets transferred straight through to the reaction, right? Make sense? So you can cut sections here. If you were to cut one right here, you would find that AC is in compression with value AX, which is what we're trying to solve. And then CD is also in compression AX with what we're trying to solve. Any other questions? No?
I'm just confused on where, like, this is happening, like, what we're solving for, like, where it's happening on the beam, I guess.
Where, on the where?
On the membrane that we're solving.
We are trying to solve for, John wanted to solve for the reaction AX. So for the reaction you want to solve, you remove the support and replace it with its quote-unquote equivalent unknown force. So, since we're solving for AX, the initial reaction that was here, you say, okay, that doesn't exist anymore. And you consider how the forces that are applied to the system trigger the system in itself. And then you look at it as if, okay, how's the reaction triggering the system separately? Does that make sense? It's kind of like saying if you were to, I don't know, it's like with thermal expansion, right? The bar is going to expand, but if you have a wall there, it can't expand. So you guys actually did this for thermal expansion when you guys found the internal forces. What you guys would do is, first of all, find what the deformation is that would be present, that would result, and then you would find the equivalent force that would cause that deformation. So that's what this is doing. We're basically finding an equivalent reaction force that would cause an equal and opposite deformation that results from the applied loads. And what I'll actually do is I'll do a thermal expansion problem with you guys using this methodology, just so you guys have a better understanding. You guys will see why you guys were doing certain things in your thermal expansion problems, which hopefully you guys will give you guys a better understanding on why we're applying certain things, okay? All right. So let's do just a quick another example. So let's say now we've got a rod here. And this rod undergoes a temperature increase, delta T, of 100 degrees Fahrenheit. The rod is, I don't know, 836 steel. And it has an area of 1 square inch. The length of this rod, we'll say, is 10 inches. Okay? Now, if we look at our tech booklets, we need some material properties. So for A36 steel, for thermal, we need alpha, which is 6.5 times 10 to the negative 6, 1 over degrees Fahrenheit. And then E, which is 29,000 KSI. Now, step 1 for this problem is identify our equations. We have equilibrium and compatibility. Well, what's our equilibrium equation? Somebody tell me. If this is A and then this is B, what is equilibrium?
It just be 0.
Not quite. We have two reactions, AX and BX, because of the temperature change.
A is supposed to be X then?
Exactly. With no externally applied forces. But we still have a problem. There's still two unknowns. So we need to apply compatibility. What you guys know is find how far the bar elongates and then determine what force would push back that elongation. That is the delta B1 plus delta B2 equals 0. Delta B1 would be like your thermal expansion equation. So I'm going to break this up again into step 1A. So let's grab this right here. And then I am just going to transfer this down to here. All right, so when we're subjected to a temperature change, delta T is equal to 100 degrees Fahrenheit. You guys would find whatever the elongation was. That elongation that you treated, if you guys remember, that lowercase delta T is actually just the change in position delta B, right? Because if you had two materials, you would need to consider the total elongation of both bars, right? You guys remember that? So how do we determine delta B1? If you guys remember, you have to use alpha L delta T. Throw it all into the calculator. And what we should get is roughly 6.5 times 10 to the negative 3 inches. You guys notice? In a similar way to what we were doing for our regularly statically indeterminate problems, we're finding a change in position of our point of interest if it were unrestrained. We did the same thing for thermal. You guys remember the steps that we did? You determined the elongation or the change in a particular point. Now, what was the second step that we did? We applied a force back against point B to then be equal and opposite in magnitude, to then find out what the force needed to be would be, such that the deformation at B was 0, or the deflection at B was 0. So we need yet another force body diagram now. This was our system 1. This is going to be our system 2, which now we can apply Bx. Now, if we wanted to find the deflection of Bx, that equation would just simply be equal to Bx times 10 inches divided by 29,000 KSI times 1 square inch. That's the NL over EA. For this case, it's very simple. You don't need to cut sections. Everyone kind of sees that the internal force in the bar is going to be Bx no matter what, right? All right. So really quickly, somebody just, actually, I'll do it. 10 divided by 29,000 divided by 1. That's going to be Bx times 0.0000345 inches per kip. And then step 1B was compatibility. So we got 6.5 times 10 to the negative 3 inches plus Bx times 0.000345 inches per kip. The only thing that's different about this now and what you guys were learning in temperature change is you guys just subconsciously just use the equations to plug in for just saying that, okay, delta is just equal to negative whatever we calculated here. Right? Now we have a formal equation for it. That's the only thing that's different, and the fact that I'm having you guys draw force body diagrams. So, really quickly, what do you guys get for BX? Because I've got something right here, but I want to make sure I've got it right. What do you guys get? Olivia, you got an answer? What'd you get?
-18.84.
I get 85 kips, but again, that's just round off error. Right, so we determined what the equivalent force would be to cause the equal but opposite deflection at a particular point. That's really all this is it's just thermal, what we were doing to find the internal forces for thermal, but instead of thermal, it's just applied forces. Does that make sense now? You guys see, do you see why we're doing kind of what we're doing? Like if you, same process. Does it make sense, hopefully? Okay. Does the steps make sense? Do I need to clarify anything further? Are there any additional questions that anybody has? All good? All right. With that said now, I'm going to ask you guys to start your get out of jails. It's only 2 different materials. It's basically almost a copy paste of the second example that we did. I'm not going to ask you guys ever to do more than probably 2 materials or 2 different force body diagrams, just because I don't feel like having you guys sitting here for an hour trying to solve the one problem. So I'll stop recording. Let me actually write this. There we go. Conduct rest of problem as typical.